Okay, in this lecture, we're going to be looking at how lenses and mirrors behave, and specifically, we're going to start with mirrors. Now, when most people think of a mirror, they think of a flat, plain mirror, the kind of mirror that might be hanging in your bathroom. And we want to look at how images form when you have a mirror, where light is reflected from the surface of the mirror. Now, if I'm standing in the middle of my classroom with all of my students surrounding me but looking at me, and I hold up a pencil, everyone in the classroom can see the pencil because the light that's scattering off that pencil is scattering off in every direction. And so here we have in this picture on the left-hand side an object, which could be a pencil or a person or anything really, but this object is sending out light in every possible direction. And some of those rays of light will strike the mirror and be reflected. Now here we have two rays of light, the red ray and the green ray, and we can see where each of them intersects the mirror, the light hits the mirror and reflects. And we know from the law of reflection that the angle here and the angle there are going to be equal to each other. And the green light is coming in, that ray of light is coming in at a different angle, but it's going to reflect relative to the normal line with the same angle. That's the law of reflection, which we saw previously. So the light bounces off the mirror and goes backwards in the leftward direction. Now, if I have my eye up here and these rays of light are going into my eye, those rays of light are being interpreted by my brain. And my brain says, okay, I've got these different rays of light that are coming in from these angles, and if I project them backwards, I can see where those rays meet. And so you can see these dashed lines here. They represent the backwards projection of the way that your brain imagines the path of the light must have been. Now, obviously, the light really came here, it hit the mirror and reflected, but your brain doesn't know that. Your brain just knows that there's this ray of light coming in at this angle, that ray of light coming in at that angle, and it projects back to see where those two beams must have come from, in other words, where they would intersect. And so that's where your brain will perceive the light as having come from. That's why you can see the image appears behind the mirror. And of course, if you move the object backwards, the image will seem to move in the opposite direction. If you move this towards the mirror, this guy will seem to move towards the mirror. In this way, the geometry of these rays of light create an image that appears behind the mirror. Now, this is what's called a virtual image. And it's called a virtual image because there's actually not any light over in this region on the right-hand side. There's no actual rays of light here. This is just where your brain thinks the object has to be based on the geometry. So there's no real light forming a real image. In other words, if you put a camera here, it wouldn't take a picture of anything except what's there. If this were a bathroom wall and it had a mirror on this side of the wall, if you went into the room over here, you wouldn't see any image over here because it's just not there. There's no actual light there to form an image. That's why it's a virtual image. That means the image forms where your brain thinks it is rather than where the light actually is. And it's kind of like an optical illusion in that sense. Now, plane mirrors are the most common types of mirrors that we see in our everyday experience, but you may have been to a fun house or something like that where you can see the images can be distorted and shaped in weird ways if you curve the mirror. And if you have the mirror be curved in a spherical shape, it turns out that you can actually use it to form images that are very similar to the actual object that the image is being formed from. And so what we want to look at is how images form with spherical mirrors. Here we have an example of something called a spherical mirror. Imagine you had a hollow sphere and you just kind of lopped off the top. And so you had just a slice on the edge of the sphere, and so you had this hollow part, and you coated the inside with some sort of reflective material like silver, and then you would have a spherical mirror. And specifically, if you had it coated with the reflective material on the left side where it's concave, you would say that that's a concave mirror. So that on the left is the concave side. However, if you coated the back side with reflective material and had the light coming in from the right-hand side, this would be a convex mirror. And that just is named for the shape, either concave, it's like a bowl or a cavity, and convex is where it's kind of flexed outward. So you can see the two shapes, convex and concave. Now, if that shape is really spherical, it turns out that there's a very special property of mirrors that have a spherical shape. If I have rays of light coming into the mirror that are parallel, and we'll pretend those are straight parallel lines, all of those lines will reflect at an angle so that they all cross the same point. Something like this. And of course, I could also have some lines coming in from the other side, and they would go out through that same common point as well, something like that. And so that special point where all the parallel rays of light would converge after reflection is called the focal point of the mirror. And the fact that all of those parallel rays converge to that common focal point, that's what enables mirrors to form images of distant objects. Let's see how that works. Now, the key idea here is that the image is going to form where the rays of light intersect after the reflection. And we have a rule. The rule that we have is that parallel rays of light always go through the focal point. So if I start with the object here and I draw a ray of light that is parallel to what, by the way? We mean parallel to the central axis here. So this central axis bisects the mirror. So this would be the middle or the center of the mirror. And this ray comes in like that. We know that upon reflection, it's going to go through the focal length. That's our rule. Parallel rays of light go through the focal length. Now, I want to draw another ray because we have a rule that parallel rays go through the focal length. The reverse must be true. Now, this guy is shooting out rays in every possible direction, but one of those rays is going to go through the focal length. And so if I concern myself with just the ray that goes through the focal length, we know the rule for parallel light goes through the focal length. So if the light goes through the focal length, it's got to come out parallel. It's just the reverse. You could imagine that if the light were coming in from here, down here, and going this way, coming in parallel, the rule is that it would have to go through the focal length. So I'm just retracing that backwards. So the light goes through the focal length, it comes out parallel. The light goes parallel, it comes out through the focal length. That's the rule. Now there's actually another line that you can draw. The line that goes from the object to the center of the lens reflects with an equal angle. And so this angle here and that angle there have to be the same angle. And you can see all three of these converge. And what we can see is that this guy here is the object, this guy here is the image, and we have an image where all of these rays of light converge. This is called a real image. And if I put a film from a old-timey camera here, like a film negative, and let the light expose it, I would have my object here, their light would fall on that image, fall on that film, and you would take a photograph. You would actually be able to take a photograph of that image. The light is actually converging there. And by the way, what I've drawn here is the converging of the flame at the tip of my object, this little candle here. I could have started in the middle or anywhere on that and drawn a similar ray diagram, and that would give me the entire image of the candle right at that spot. And again, that forms what's called a real image. So let's look at those rays again real quickly. So the first ray is a ray that is parallel to that central axis. It's called the optic axis if you want to get technical, but this ray comes in parallel to the central axis and it reflects coming out through the focal length. The next ray goes through the focal length it comes out parallel. And then we can look at all three of the rays. The last ray is the one that goes to the center and reflects with an equal angle, and all three of those rays converge. Now, when you're actually trying to draw these things for yourself, don't try to draw all three rays. It's actually kind of tricky to do that. You just need two. You just need to find where those two rays intersect, and that will locate where the image falls. Okay, now this distance to the focal point right here, that is the key distance that we have to know about the mirror. And so if we know that, and I tell you where I've placed the object, I can actually calculate where the image will fall. And vice versa, if I tell you where the image needs to be, I can tell you where to place the object so the image forms there. And the way that we do that is with a very simple equation called the mirror equation. And this works for spherical mirrors. That equation is this: 1 over the object distance plus 1 over the image distance is equal to 1 over the focal distance. And those distances are measured to the center of the mirror. So for example, here's my image. So from right here to there, let me draw that in. I'll draw it in green. So if I start here and I go all the way across to the center there, that would be the image distance. Now this distance up here, I'm going to draw in yellow, that would be the object distance. And again, it's the distance actually to the center of the lens. So that distance is the object distance. The green one is the image distance. And you would just plug those guys into the equation, and or plug in the ones that you knew to solve for the one that you didn't know. Now there's one other equation that is also very useful when looking at that, and that's the magnification equation. So look at these two things. We have the image here and we have the object there. Can you see that the object is a little bit taller than the image? How much taller? Is it twice as tall? Is it 3 times as tall? Well, we can figure out how the size of the image relates to the size of the object through the magnetism equation, which is m equals to the height of the image over the height of the object. So if the image is twice as tall as the object, that means there's a magnification of 2 to 1, and you have a 2-factor magnification. Now, there's some geometry between, because if we look at the height and we look at the distances, they make triangles. So if I consider the distance here to the object and the height, that's going to make a triangle. And by doing a little bit of geometry with similar triangles, you can find out that this equation is also equal to the image distance over the object distance. Now, for reasons that we're going to see shortly, when you actually calculate the magnification equation, you want to have a minus sign in there. And that's our sign convention, which we'll explain in a little bit. But this is how you calculate the relative size of the image to the object size. And of course, if you get this number is bigger than 1, that means that the image is bigger than the object. On the other hand, if the image is smaller than the object, you're going to be dividing a smaller number by a bigger number, and that would tell you that this would be some fraction. So if this number is less than 1, if it's 0.5, that tells you that the image is half the size of the object. And of course, if it's equal to 1, that means the image and the object have the same size. Let's see how this works in practice with an example. We'll consider a concave spherical mirror with a focal length of 10 centimeters and an object distance of 30 centimeters. So I've drawn my little picture to build my ray diagram. And so I've drawn my mirror, and I've located the focal the indicated where the focal distance is, and then the object, if this is 10, the object is going to be at 30. That means it's 3 times as far out. And so I've located my object there, and here's the center of my lens. And this point here is the focal distance of my lens. Now the first ray that I want to draw is the one that is parallel to the optic axis, And we know if that ray is going like that, it's going to reflect, and it's going to go in a straight line. And usually when I try to draw these, I actually do it with a straight edge, like a ruler. And so this is going to be a parallel ray, comes out and it goes through the focal point. Now the other ray that we can draw, one of the other, well, we can draw, we've seen how to draw 3 different rays. We only need 2 of them. Which ones you pick are personal preference. I like the one that goes through the focal distance, and that's going to come out parallel to the optic axis. And we know where those rays cross, that is going to be where the image forms. And so we can see that the image is going to form right there. And that is a real image because we can see both of those rays of light intersect at that point, and the rays of light are all the rays of light are passing through the image. That's how we know it's a real image. Now let's apply our equations that we saw to calculate the actual location of that image and also its magnification. How much larger is it, or smaller? Okay, so the equation that we saw in the last slide was 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And what we want to do is actually solve for the image distance, because that's what we're trying to find. We're given the focal length, we're given the object distance, where is the image going to form? That's di. So just with a little bit of algebra, moving this do onto the other hand side, we get that the reciprocal of the image distance, that 1 over di, is equal to 1 over f minus 1 over do. Now we can simply plug in our numbers. So if we plug in the values for f is 10 centimeters and the object distance do is 30 centimeters, we get that 1 over di equals 1/10 minus 1/30th. And of course we can get a common denominator for that, which would be 30. So that would be 3 over 30 centimeters minus 1 over 30 centimeters. And that would give you 2 over 30 centimeters is 1 over di. And of course, if I take the reciprocal to get di by itself, that means that di is going to be 30 centimeters over 2, or that di is equal to 15 centimeters. And we can see that if I look at my ray diagram up above, the image forms about halfway in between. So my ray diagram is actually showing that my math is spot on. The two are very consistent. And so I've got my 15 centimeters here as where the image forms. Now one thing that we can note that this 15 centimeters is actually positive 15 centimeters. And if the image distance is positive for a mirror, that tells you that the image forms on the same side as the object. With a real image, we expect the image and the object to be on the same side of the mirror. And so that's considered the correct side. And if the image forms on the correct side, it's going to be positive. If instead the image appeared over here somewhere, that would be the wrong side of the mirror, the one that would not be correct, and that would be a negative distance. And so if you end up with a negative distance in your calculation, that just tells you that the image is forming on the incorrect or the wrong side of the mirror. Now let's look at the magnification. We have the formula, the magnification is equal to minus di over do, and so that's going to be minus 15 centimeters over the object distance, which is 30 centimeters. And so that's going to be negative 1/2. And so we expect the magnification to be a factor of about 1/2. Now, if I look at my ray diagram up above, I can see that my image does look smaller. Is it exactly 1/2? Not really, but I can see that it's definitely smaller, and that makes me feel confident about my calculation because, I didn't have a straight edge here. I didn't draw this perfectly. If I had been very, very meticulous, it would be absolutely spot on. But you can kind of see that it does suggest that this relationship is correct. Now the last thing that I want to mention here is the minus sign on the magnification. We already talked about what the minus sign on the distance means. The minus sign on the magnification means something else. It means that the image is inverted or upside down. And we can see in the ray diagram up above that indeed the image is upside down. If the magnification had been positive, it would mean that the image is right side up. And that's how we can use these equations to calculate what the image distance is going to be, what the magnification is going to be, and we can use the ray diagram as a check. So if I drew my ray diagram and I ended up with an image that was right side up and I calculated a negative magnification, that would tell me that I did something wrong, or vice versa. And of course, in this particular example, I gave you the object distance, I gave you the focal length, and I said find the image distance. If I gave you the object and the image distance, I could tell you, you could tell me what sort of focal length would be needed. If I gave you the image and the focal length, you could tell me where to put the object. The math is just the same. This is the equation, this is the mirror equation here that we're going to be using, but you can use it to solve for whatever is the unknown in the problem. Now here we have a different situation. We have the object which is located inside the focal length. In the previous example, the object was outside the focal length, out here somewhere. But here, the object is inside the focal length. In other words, it's very, very close to the mirror. And what we see, if we follow our rules for drawing rays, the image forms in a very different way. Now here I have three different rays drawn. The first ray that I'm going to pick out is the ray from the candle tip up here. Now that ray is actually along the line from the focal length. So if I extend this line here, if the ray of light were coming in this way, we know that when it hit the mirror, it would reflect in the backwards direction. Now of course the ray's not coming from down here, but it's coming on the same line. So if I look at that candle, the ray of light coming from the candle along the line from the focal length is going to reflect out parallel, and that's what we expect. Now the other ray that I've drawn is the parallel ray, and we know that when it reflects, it's going to come down through the focal length. And then the third ray that we could draw is the one to the center of the mirror, and it's going to reflect with the same angle relative to that central optic axis. And so any two of those three is sufficient to draw. Now, keep in mind, what's going on here is that your eye is out here somewhere. Here's your eye seeing all these rays of light coming in, and your brain is projecting the direction of those rays backwards, and where they intersect, right over there, that's going to be where the image forms. And so we can see a few things about this image straight away. First of all, it's right side up. Second of all, it's greatly magnified, but the most prominent feature that we see is that it's on the wrong side of the mirror. And so what does that mean? That means that we would expect the image distance to be negative. But this is how we can use these different rays to figure out from our ray diagram where the image is going to form. And again, we can use our equations to calculate where that image is going to be, how big the magnification is going to be. All of those things are possible with that equation. And let's take a look at that on the next slide. Okay, so let's look at an example with the focal distance of the mirror being 10 centimeters and the object distance being 5 centimeters. In other words, the object distance is closer to the center of the mirror than the focal distance. In fact, it's half as much. So if I draw my mirror, I can put in my focal distance, which is at 10 centimeters, and I can put my object about halfway in between the mirror and the focal distance, because I know that's supposed to be at 5 centimeters, and I can draw my ray diagram. Now, the first ray that I want to draw, the one I always like to start with, is the one that comes out parallel to the optic axis. And we know that the ray that is parallel to the optic axis is going to reflect and go through the focal length. So I've drawn that in there. The next ray that I've drawn, the blue ray, is the ray that's on the line, the straight line that goes from the mirror through the object and to the focal point. So I've got the line from the focal point to the tip of the object. I've extended that with that blue ray to the mirror, and we know that that's going to reflect out and come out parallel to the optic axis like that. And again, we can see that these rays are not coming together. They're spreading apart. They're diverging. And so if my eye is over here trying to find where is that image formed, it's going to imagine these rays being projected backwards. So this one's going to project backward like that. The red one's going to project backwards like that. And where they cross, that is going to be where the image forms. And so we can see that this is not a real image because the rays of light are all on the left-hand side. The image forms on the wrong side of the mirror. And so that is what we expect. And calculating where that image is pretty easy. We still have that same equation, and when you solve for the image distance, just like we did before, you get 1 over the image distance is equal to 1 over the focal distance minus 1 over the object distance. And we have that the focal distance is 10 and the object distance is 5. So that's going to be 1 over 10 centimeters minus 1 over 5 centimeters. Now, get a common denominator. That's going to be 1 over 10 centimeters minus 2 over 10 centimeters. And that works out to be minus 1 over 10 centimeters. And again, that is 1 over the image distance. So if I flip that, I get that the image distance is just simply minus 10 centimeters. Oops. And what does the minus sign tell me? Again, for the distances, the minus sign tells me that the image is on the wrong side. We expect the image to form on the same side as the object, but here we see the image is formed on the wrong side of the mirror, and that's what that minus sign is telling us. If we calculate the magnification, m is equal to minus di over do. That's going to be equal to minus, what's the image distance? That's minus 10. And it's actually centimeters, but the units will cancel, so it doesn't really matter. Minus 10 centimeters divided by the object distance, which is 5 centimeters. And the minuses cancel, so we get that minus and that minus cancels. And we end up with the magnification equal to 2. It's a factor of 2. And we can indeed see that the image is significantly larger than the object. And so the magnification is a factor of 2. It's twice as big. And also it's positive, so that means it's upright. If this were negative, that would mean the image were upside down, but since it's positive, we know that it's upright, and we can see in our ray diagram that we indeed get the math predicting what we expect. And that's how we can handle concave spherical mirrors, and that's one of the things that we're going to be looking at as we go on.